Hello everyone, Vipul here. Today, as part of our data structures and algorithms course, we are going to look into another data structure called as binary search tree. And we will see differences between what is a binary tree and what is a binary search tree and what how we are going to implement that particular data structure. Before going into the lecture, so first of all, I'll just give you a brief intro about Newton School. Newton School was founded by IIT grads, and they have a positive motto saying that uh, to help the people, those who are really not familiar with all the topics that are necessary for a software engineer, and they also came up with a very good initiative called Launchpad, where we are making up a beginner level courses for free on YouTube. Okay, so if you want to register onto Newton School, please visit the website and just fill up your details here. And on clicking on the sign up, you will be able to register onto the you will be able to register onto the website. Next, once you have registered onto the course, once you have registered onto the Newton School, you'll be able to see all these things here. So inside the Launchpad, you'll be having several courses that are going on. So if you see, there is a course called Introduction to Node.js by Nehru Permalla, and if you just open this particular Launchpad, you will be able to apply it using filling up your details. And once you have applied and once you have registered into this particular launchpad, that track will be available here. So I have already registered into a course, Introduction to Data Structures and Algorithms. You can just click on once you have registered, you can just click on that particular course, and all the lectures that are necessary for the course will be available here. And if you have any doubts, you can just make those doubts uh, here inside add a doubt, and you can just put up your queries here. Your doubts will be resolved within a minimum time. And also we have integrated a coding environment where user can just simply create his own code environment, and you can write the code whatever you want in which language you want, and you can see the input and output of that particular thing. So it is more like you can play with the stuff that you want around here itself inside the website, rather than working on the some other platform or making it in on your local machine. Okay, so this is a quick intro about uh, how to use and how we are going to deal with like the coaches and all. All right. So coming back to the lecture, yesterday we discussed about the priority queues and how we are going to implement the priority queues. How we are going to use. We had an implementation of match PQ, and so until yesterday, whatever we have discussed, it is something like arrays, linked lists, queues, stack, priority queues, right? This all comes under the linear data structures. It means that all the elements that we have are stored in a linear fashion, where uh, in a one go you can just iterate through all the elements and you can check like what are all the elements are present. But we also have an other uh, a category called as nonlinear data structures, where we are going to start it today. It is simple and easy. That is called as a for example, we are going to take the data structure to be discussed as trees. Okay, we also have other one called as graphs, but we are not going to cover up this in the launchpad, but we will be able to do if we have a full-time course with DHA. Okay, so for a beginner level, trees are enough, right? So okay, I'm saying non-linear data structure. It means that the elements that you're going to that will be shared and stored inside this data structure will be in a non-linear fashion, where it is not like in a sequential manner, and you need to go in a different ways to print all the elements that you have inside. So we generally call it as a traversal inside that particular tree, inside particular data structure, where they are not stored in a linear fashion. Okay. All right. So before going into trees, what is a need of tree first of all? So until yesterday, we have discussed all the data structures which were storing all the elements in such a way that we are storing only a single value at particular next, right? And we are also giving some type as well for that, because most of them were arrays, and even in the linked list as well, we are going to give the data that we are storing a type, right? Most probably we have dealt only with the integers type. All right. So there is a necessity for storing up the key value pairs. Okay, key value pair, what does it actually mean? Key value pair is nothing but it is simple, like if you want to store uh, something like what we call it as, it is something like you can just take an example of your phone book or contact book that you have in your phone. If you just open, and when you're saving up a contact or your friend's number, you'll just give a name and a number, right? So what is it is doing? It is simply storing up the key value pair there. It's a simple real time example. So is there a necessity of a symbol table? Yes, for sure. In real time, you will be dealing with many kind of key value pairs. So there should be a data structure which will be implementing this kind of key value pairs. All right. So we always insert a value with a specified key, and whenever you want to know the value of that key, we will just make a search, and we will get the value of that key stored. And uh, and in a symbol table, generally, if the same key is being inserted again, then it will be overwrites the old value that we have already. Okay, so that is a simple concept of a symbol table. So one of the prime examples, and in real time it is very much important for us to use is in a DNS lookup. Most of them know, I hope. Domain name systems, domain name server, where there will be stored with the URL and also its IP address. The DNS will be having this the list of all the URLs and and the corresponding IP addresses. These will be stored in a symbol table. All right. And also simple example of a dictionary. If you want to find out any word, we will search for that word, and that word will be having a proper definition. So word can be considered as a key, and definition can be considered as a value. So this is a basic overview of symbol table. So now you got I hope you got a clarity like why symbol tables are required. So these are some of the real time examples where it is already in use. All right. So in how many ways we can implement a symbol table, right? We have different data structures, and how we are going to implement and make make use of that particular symbol table. So we have two simple ways. One is sequential search. It is nothing but using an unordered linked list, where we will be storing all the elements, and how we are going to store the linked list. Okay, we'll just keep on adding the elements, right, one after the other. And what happens in this case? In a sequential search, if you are going to store at every node, we will be storing the key, the value, and the next node as well, right? Earlier, when we have discussed, we have just only stored the data. Now we are storing the key and value, both parameters. We can do that, right? It's not a wrong. Okay. So what is the worst case scenario for a sequential search? Sequential search of a linked list is definitely the search will take n in the worst case if the element is at the last index, at the last element as a last element. Even the insert will take uh, even the insert will take, if you're going to add from starting, if you're from, so like the pointer is at the starting and you need to insert that element at the end, so it will take n there. So in average case, it might hit a randomly. It might be done within half of the length of that particular linked list, right? Is that an ordered iteration? No, because it is an unordered list. We are not maintaining any order when you are inserting. So that is a simple sequential search unordered list. Okay. Next one is a binary search ordered array, where you're storing the elements based on a binary, based in a sorted order. Okay, whenever you are inserting the element, then we will be making the insertion make sure that it will follow an ascending order. Okay, in that way, if you're going to do also, the insertions may take n, but the search will take log n, because we will just check with the middle index first. If it is lesser, if the value that you're checking is lesser, we will go to the left. If if the value that you're checking is greater, then we'll go to right. So this is how the two basic implementations of symbol table works, which is sequential search, unordered list, and binary search, ordered array. So can we make some good implementation, and can we make it much better? Yeah. So there is another data structure which we uh, use in like which will be which is really important and which will be necessary for you to learn when you're learning algorithms and data structures, because we are going to make it a bit more faster than the sequential search and binary search implementation that we have a symbol table. Okay, that implementation is called as binary search tree. Okay, binary search tree. It is different from binary tree. So, okay, how it is different? In a binary tree, we don't follow any order. We will just simply insert the elements on left and right, like how we did in a heap or in a priority queue. Yesterday we discussed about binary heap. Those who haven't watched the video that we have that is which is a previous lecture that we have discussed about priority queues, please watch that video and then continue this, because yesterday we discussed about binary heap and binary tree as well. Okay. So inside a binary tree, we are not going to maintain any kind of order when you are inserting. Okay. We will just simply insert an element on the left side, right side. Again, we will go for the next level. Again, left, right. In that way, we will be inserting all the elements. We don't follow any order. But in a binary search tree, we follow an order which is called as a symmetric order. Okay. Cool. We will follow a symmetric order. It means that every node will always maintain a rule that all its left side elements will be lesser and all its right side elements will be greater. Okay. Always for every node, all its left side elements will be greater. Left side in the sense left subtree will be greater, all the elements on the left side will be lesser and all the elements on the right side will be greater. So this is the basic rule that we maintain when we are dealing with binary search tree. Okay, cool. So as we discussed that we are going to deal with key value pairs. So how are we going to store? So every element in the BST is stored in a node, like how we discussed in a linked list. Here also we are going to store these elements in a node. Okay, what all data will be stored inside a node? Node will consist of key, value, link to left subtree and link to right subtree. Simple. If you just compare the linked list that we have implemented already, inside that we used to store only the data directly and the next link, right? Here, but we are storing the left link and also the right link, because we need to maintain the fashion that all the elements on the left side should be lesser and all the elements on the right side should be greater. That is the reason we maintain the link for the left and right as well. So, all right. Do we maintain any indexing or do we have any array inside the BST? No. We are implementing the BST having the reference only with the root node. Okay. Clear? Yep. So, all right. So, what all operations that the BST have? So, if you want to store the elements in a simple table, what all we can have? It is simple like putting those elements. It's also simple, simply getting those elements, right? So, we call them as insertion and searching. Insertion. How we are going to insert the elements? Simple. If the element is lesser than the current element, you will go left. If the element is greater than the current element, you will go right, because that is what the principle, right? All right. If you find that key already, if you find out that key that you want to insert is already present in the tree, what we are going to do, we will just reset the value. That's what we have discussed. I hope all of you have already used hash map when you're writing some code for in Java or a dictionary in Python. Okay, so these are also called as a symbol table implementations, where if you are trying to insert the key that is already present in the tree, it will just override the value that it is already have, right? So if the key is not present, then we are going to insert that key. Simple. That is the insertion. Next, coming to search. How the search will be happening? Same. It will check whether the current element is less than the element to search or not. If it is less, then go to left. If it is greater, then go to right. If that element is if you find out that element is the key that you're finding is equal to the current key, then simply just return the value that is there. If you didn't find any, just return the null. Okay, these are the two basic operations that we have inside search and insert, right? So this is a quick overview of BST. Then we will try to do it with we will try to take an example and we will insert. All right. So we say that now we are going to maintain that order, right? So I'll try to insert some characters, like something like characters or letters into the BST, and let's check how these elements are inserted. Okay. Okay. First element I want to insert is T. All right. One element is inserted. So there is no root at this point. So now this element will be maintained as root. All right. Super. So next element I want to insert is O. Okay. So what half the insertion will be happening? First of all, it will come at the root node. It will check O is less than T or O is greater than T. O is simply lesser. So it will come at this particular node. Here, do we have any node here? No, null. So we are going to insert O here. Simple. So you can assume that we are having the values like the T is the key and 1 is the value. O is the key and 2 is the value. Simple. I'm just inserting the value as the incremental order as a number of elements that we are going to insert into BST. Okay. O is inserted. All right. Next element to be inserted is N. Okay. Again, N, it will start from root node. It will check n is less than t. Yes, n is less than t. It will go to the next left node. It will check is n is less than o, m and o. Yes, n is less than o again. So it will just check to the again. It will go to the left. There is no node present here, and n will be inserted. It is having a value of 3. Awesome. Next element that we want to insert is y. We will check again from the root node y is present, y is less than t or y is greater than t. Y is greater than t. We will go to this way, right? There is no node present here, and I'm going to insert y here. It is having a value 4. Awesome. This is how the BST will insert the element. So if I want to get the element n, I want to get the value that of n. What it will do? It will start from the root node. N is less than or greater than t. N is less than. So it will traverse to the leftward. It will go here. It will check again n is less than 0 or greater than 0. N is again less than 0. Sorry, O and n is present again, it will go to the left node. Here, n is greater than, less than, or equal to 0. N is equal to n, right? You find out the node that it is equal with this key that you're searching for, and it will return the value that you want. Simple, right? It is simply inserting the element and retrieving that element. All right. Just putting up the values and getting up those values. All right, that's fine. So we are going to write the code for BST then. BST. All right, so class, we need to select our language, right? We will be writing our code inside Java. All right, class main. First of all, writing up the code for main. First of all, static, public static void main and string args. Okay, this is the main method. We will come to main method later, but we need to start, first of all, write the code for our BST. All right. So as we discussed, BST will be storing up key value pairs. Super. So are you want to make that BST will work only for predefined data types, or will your BST only work for a single data type? No, we should not make that kind of data structure, right? It should not. We can't implement an data structure and say the users to use only for this particular type. You could not do that. You need to make an what we call the data structure in such a way that everyone can use it, and then any kind of application they can use it if there is a necessity of a simple table. So I'm making it as a generic. And how we are going to write the generic, you can write with any of the value inside it. I mean, I'm making it as a key and value. You can make anything if it is required. So I am making my key as comparable because I need to every time make it compare, right? It need to compare with the other elements. Okay, so that is the reason I am making that generic type as comparable. Comparable, those who didn't know the comparable is an interface where in Java it is a built-in interface where we can just, it will have only a single method called as compare to. So if you're using up your own user defined data structure, you need to write the compare to method. If there is no if you are using a inbuilt data type or a primitive data type, which is nothing but a string or an integer, it will take care of that compare to method. Okay, it will compare the, if you insert a string, it will compare those two strings, and if you insert the numbers, it will compare those two numbers. And I am inserting the value as well. So what is the type of our BST elements? It is something like key, which is of type key. I'm just saying it is I'm just giving the name as key because it need to be a type of generic. Okay, and value, which is of type value. All right, I'm just giving the name there. Okay, you can just keep k as well and v as well, no issues in that. Super. So all right. So we discussed that BST will be consisting of what elements, where the elements will be stored inside a node, right? So I am maintaining an inner class inside saying a node. So, okay, good. Inside a node, what all we are going to store? They will be storing key, we'll be storing value. Keys of type which, keys of which type? Keys of data type, key, because we made that as a generic one, right? And don't get confused, I'm using the same variable name as key as well to avoid the confusion. Value, val. All right. And what all we need to store when we have a node? We need to have the left link to the left subtree and right link, which is to the right subtree. All right. Node left. Next one, node right. Awesome. So when we are creating a node, we will get key, we will get value, and we are just assigning it to our key and value as v. Simple. And left will be, when we have created the new node, the left will be null and right will be null, right? I'm maintaining the null as well. Super. So what we did until this point, we have created a class BST, which will be having like two types inside that. One is the key type, the other one is a value type, because we are going to make it generic. And inside that we have used the node class, which like, because BST consists of all the nodes. Inside the nodes, we are going to have key, value, left link to the left subtree, right link which is to the right subtree. Awesome. Next, so what is the reference point for a BST? BST having a reference point as simple node, because that is the only, like how the linked list used to have the head. In a similar way, the BST will be having the root as a reference. Okay, that is only reference that we have when you want to traverse through BST. Super. Right. Next, how we are going to insert the element. Okay, when you are inserting, you will get key and value. Okay, whenever you are inserting an element into BST, they always give you the key value pair, right? So I'm getting key and also getting value. How we are going to insert that? I am trying to make use of a helper method where I am passing my root, the key I need to insert, and the value I need to insert. We will see why this helper method is necessary for us. Okay, because I am going to write the uh, put method using the recursion. Okay, so once it is inserted, what it need to return? It need to return that node, right? If not, how, where you will be storing? So I am making that to be stored in the root. All right, because that is the reference point that we have. So what it need to return, it need to return a node and put of, I'm getting a node here, which is something like X, and we're inserting key here and value val. Awesome. So how were we going to insert? Simple. First, we need to check whether this particular X is null or not. If it is null, it means that there is no node present until this point. New node of key comma value. It will create a key and it will return it. Where it will be returning? It will return to this step and it will create a root node. Okay. Now the important point is we need to compare the current key that we are insert, the current key that we have, I mean the current node at which that we have, and the element that we need to insert. We need to compare both of them, and based on the value, if that is a lesser, it need to traverse to left side. If it is a greater, it may need to traverse to the right side, right? So as we discussed already, we have used a comparable where we have extended it. It means that we can inherit the properties of that comparable interface, where simply key dot compare to of x dot key. What are we doing in this step? We are simply making a comparison between the current node and the element need to be inserted. Okay, to comparing the key with current key. All right. So what the compare to method will return? Compare to method. For suppose if you are comparing something like A and B, if A is less than B, it will return -1. If A is equal to B, then it will return 0. If A is greater than B, then it will return 1. All right. If CMP is less than 0, what we need to do? We need to traverse to what we said, we need to traverse to left side. And what if the like comparison is greater than 0, then it need to traverse to right hand side. What if the key is already present? It means that then if you want to insert the element as yes, and s is already present inside the tree, what it will do, it will give cmp as 0, right? In such a case, we are going to just update the value of that key. How we are going to update? The current node x dot value equal to the value that you need to insert. All right. So, right. So how are we going to traverse to left side and right side? How are you going to do that? It is simple. We can just call the same method that we have written by saying x dot left, key that you need to insert, and value, right? Again, put x dot right, key that you need to insert, and value. Okay. If you write, like if you do the same this thing, it will be recursively calling up the function until and unless you find a node as null. That's okay. But once you find out the node, and if you have written something from this new node, where are you going to store that? It need to store in a particular value, right? You're just making a recursion. That's all right. But where are you going to store that link? You need to store somewhere. We will be storing that on the left side of the current node, because as it is lesser, that particular node that you need to insert is lesser, it need to be stored on the left hand side, and that need to be attached to the current node, right? How we are going to attach that? It is using x dot left, because until this point x dot left will be null. Now the same thing for right as well. Simple, nothing confusing. That last x dot right will be null again. So at last, after inserting this thing, we need to return the x, because at the end point it will be returned to the root. That is the reason we are returning the x value. All right. This is how the put works. Simple. In a similar way, if you want to start doing the same thing for get as well, what the get will return the value, which is of type value, right? That is the reason I'm making it as value. So what the get need to take, it will take up a key and it will return the value of get. Simple. I'm also writing another helper method for the get, It is simple like get where I am passing up the root and the key that I want to check. Simple. Right. So how we are going to make this happen? Value we are returning and the helper method for get same node x and key that you want to find out. Good. So same. How are you going to find out if x equal to null? Return null. It means that particular node is not present. If you're checking it for again cmp equal to key dot compare to of x dot key. What does it do? It will compare the key that you want with the current key. It will compare because we are starting the iteration with root. Always remember, we always start the iteration with root because that is the only reference that we have when you are dealing with a BST. Likewise, in a linked list that how we have a head, in a similar way, we used to have the root here. Same. If CMP is less than 0, return get of call in a recursion manner, it will traverse to the left side. You need to check key, else if CMP is greater than 0, then return get of x dot right and key. If the key is greater than the current key, then you need to go to the right hand side. That is right. Else, if you find out the key, just simply return that, right? Return x dot value. Simple. If it is lesser, traverse to the left side. If it is greater, traverse to the right side. If it is equal to, then you need to pass on the return that value, right? Okay. We will check our implementation. So I am creating an object for BST. So we discussed that the type you need to give here itself. So I'm giving it as string, comma, integer, and BST equal to new BST. I've created an object. BST dot put of something like a D. I want to insert element as 3, or I'll just simply insert the elements in an order where 0. BST dot put of x 1, BST dot put of plus 2, dxs. All right. So now if you want to print the get, or if you want to print the get of that BST dot get of, I want to get yes. All right. Okay. Let us run this code. Command minus, yeah. So this is the complete implementation. Just try to run this code. Let's see what it will return. Just a second. Let's see whether it is whether the put is working or not. At this point, we will check. BST dot root dot key. We are getting a null point exception at 61st line. There is no need to a constructor inside the BST. At initial stage, the root will be null. Calling up this method root, where root is null. Return the new node with key and value. Oh, sorry. I have created the node here, but I didn't return it. So that is the reason it is showing up there. All right. So now it happens when you're dealing with this kind of thing. So if you see, I have inserted D, X, and S, and I'm getting the value as S, so it will return as 2. If you want to ask for the element which is not there, it need to return null. It return null because that element is not present in the, it is not present inside the tree. And if you check for t, it need to give the value as 0. Awesome. So this is the normal put and get implementation. If you want to traverse through the BST, we have several traversers where we call as pre-order, post-order, in-order, level order, as we discussed. So this is how the trees are inserted, right? So if the level order is something which it will first of all print the elements on the first level, next with the next level, the next with the next level. So in this way, it will the first it will traverse through T, next time it will traverse to O and Y, next time it will traverse to En. So we have 3 levels here. So this is a simple implementation of binary search tree, and I have given an assignment for this lecture, including which will ask you to implement uh, the traversals that are necessary when you're dealing with the like BST. So we have several orders, something like pre, post, and in. It is nothing difficult. I'll just type it here. It is simple. Inside the pre-order, what we do is pre is something like always print parent first, after that left, after that right element. Okay, that is a pre-order traversal. Post is something like first print left element, right element, and then print the parent. Okay, and next in order is something like print left, parent, right. Why it is called as in order? Because if you see the element, the lesser element will be on the left hand side and righter element will be in the right hand side, right? So left side, so first, and then the parent, and then the right side. So if you do this in order, it will be, if you do this in this fashion, we call it as an in order because when you print the elements in order, all the elements will be printed in a sorted order. Okay, and pre because the parent is first printed, so we call it as pre-order. Pre parent will be printed first. Post because the parent will be printed at the last. That's the reason we call it as post order. The other one is level order. Like how I said right now, it will print the elements in a level by level. Like at this point, at the first level we have T, in the second level we have O and Y, in the third level we have value as N, right? So there are 3 levels in the in this binary search tree, and level by level the elements will be printed. So these are the 4 basic traversals that we implement when we are dealing with BSD. We have some other views as well, some other traverses as well, but these are the basic things that are enough for us at a beginner level. Okay, so this is about the thing, right? So what is the time complexity that we are taking up when we are inserting an element, when we are getting up that element? Okay, so whenever you are inserting the element into BST, in an average case, the time taken is log n, because you will just traverse either on the left side, either on the right side. You won't traverse throughout the array, right? Okay. So average case will always be log n for insertion or search. Both the operations will always give you within an average case of log n. Good. But what about the worst case? Worst case might definitely take up to n, because if you are inserting the elements in unsorted order, simple, just think that you are inserting the elements which are already in sorted order. Something like you have inserted A. Next, if you want to insert B, if you want to insert C next, if you want to insert D now. So in this fashion, if you're going to insert the elements, it will definitely take the worst case as n. We have some more improvements for the BST. We call them as balanced binary search trees, where we will always try to balance them. We call them as binary search tree, balanced binary search trees, or AVL trees, or red black BSTs. RBBST, red flag BST. So we have some other improvement for the same BST that we have discussed right now. But to do all those things, first of all, you need to be very clear with the BST concept. Then, if you please try to implement these data structures that we have discussed on your own, that will uh, uh, help you much when we are dealing with advanced algorithms that, or the data structures that we have. Try to take up the like open up the IDE and just write the code for BST that we have discussed. Implement that on your own. We also have delete method, but I didn't discuss here. That might be a little bit confusing if I discuss at this point itself. Try to, if you want to learn, you can just open up and Google for that, and you will find many resources out there, and check with the delete method. When we are deleting, we need to check with some of the a couple of cases when you're deleting an element. And right now we just implement put and get, and then try to check like how much time it is taking up for the when you're inserting more and more nodes inside, and how much space it is taking. Okay, so this is how a simple BST works. And we also discussed about the difference between binary tree and binary search tree, right? Where binary tree doesn't maintain any of the symmetric order, but binary search tree always maintains a symmetric order. Because of that symmetric order, most of the times in an average case, it will always give the results with an average case of a log n time, where binary tree always take n time. Binary, it's simple. The binary there defines it as something like every node having two elements, right? Two children, simply. Okay, so always there is a node, and it will be having two children, whether which will be one is on the left side, the other one is on the right side. In binary tree, we don't maintain any order, but in a binary search tree, we maintain a symmetric order, where all the elements which are lesser will be on the left hand side, and the elements on the right will be on the right. Elements which are greater will be on the right side. So this is all about binary search tree. So if you want to enroll into any of the courses, you have the links below in the description. Just um, click on any of the link, and you will be having the good content in your hand. Thank you all.